Okay, let's start here. So we started with molecular orbitals, right? And we have done sigma and pi bonding under the molecular orbitals. Agreed? And then after that, I'm just recapping of what we have done in the last class. And then we talked about, I'm going to that particular screen where I explain that the reactivity of the covalent molecule depends on these three factors. I told you that the reactivity of the covalent bonds depends on the polarity, depends on the strength, and depends on the bond type. So we have done the bond strength and we have done the bond type, that was sigma and pi. So the A concept, the A part was still left out. So we'll be continuing with this polarity part. I hope I'm clear. Now, what is polarity? And we are talking about the covalent molecules, right? We are talking about the covalent molecules, and we know that these molecules are basically sharing the electrons. If we talk about the chlorine and chlorine atom combined together, covalently bonded, so we know that they both are sharing their pair of electrons. So this chlorine has got the 7 electrons and it's sharing one. This chlorine has also got the 7, and in order to complete it octet, it's sharing this pair, this particular electron. Okay, so that is what we are aware of, right? So they both are basically sharing. So the same pair of electron is revolving around this particular chlorine as well. Okay, around this chlorine, and the same pair of electron is revolving around this chlorine. Then where does this polarity comes from? So from our understanding, from a previous understanding of ionic compounds, we know that if I talk about sodium chloride, I have a sodium ion and I have a chloride ion. Now, these ions are formed because sodium has transferred its electron to chlorine, and chlorine has accepted that electron. So, what is happening? The sodium has formed a sodium ion and the chlorine had formed the chloride ion. So, they both are opposite in nature. Okay, one has positively charged, another one has negatively charged. So they both have a strong electrostatic force of attraction between them. So this kind of a molecule we can easily say polar, because one is positively, another one is negatively charged. So it's understandable in the case of ionic. But what about covalent? When we have the same amount of the same type of atoms combined together covalently, or even if we don't have the same atoms, like in case of HCl, then where does polarity come from? Okay, this is a question, because they clearly say that the reactivity depends on polarity. So let's talk about what makes the covalent molecules polar. Now, in order to understand what makes a covalent molecule polar, that means polar means it's same like we have a north pole and we have south pole. One is positively charged, another one is negatively charged. So there should be something between these two atoms or between these two atoms which give them slightly polarity. One becomes slightly positive, another becomes slightly negative. Or if they are not polar, then they will be said non-polar. If they are polar, they will be said as polar, right? Am I clear? So what is the concept that make them polar or non-polar? So here comes the first terminology which we need to understand. That is basically electronegativity. Have you heard of this terminology before? Now, let me explain you. So when we have tug of war, have you heard of tug of war? That's a kind of a sports event. When we have a tug of war, what happens? There's a team on this side and there's a team of few players on this side, and there is a rope they're pulling to it. And on this rope, there is a ribbon there, and there is a line. Okay, and they try to pull the rope towards the self along with that particular ribbon. If this particular team, a team, try to pull the rope towards itself, then they is said to be winner. So same happens in the case of covalent molecules as well. So but that pulling depends on the strength, isn't it? If A is stronger, so A pulls to the ribbon, the rope, uh, where the ribbon is being tied toward themselves, right? So it all depends on the strength of the team. So here also we talk about the strength in the case of polarity. So in a way, we say that the electronegativity is the ability to pull shared pair of electrons, okay, towards itself. So if we have the shared pair of electrons, right, like for example in the case of hydrogen and chlorine, so this is a shared pair of electron. So whichever element will be more electronegative, okay, whichever element will be more electronegative will be pulling, it will pull shared pair of electrons, shared pair of electrons towards itself. Okay, let's say chlorine is more electronegative. So this shared pair of electron will be pulled more towards the chlorine. Because it will be pulled more towards chlorine, so it will be acquiring partially negative, and the electrons will be moving away from hydrogen, so they will acquire a partially positive charge. When this happens, then we will be saying that hydrogen chloride is a polar molecule. Okay, is a polar molecule, right? So the polar molecules are basically the molecules which are polar in nature. Okay, the molecules which are polar in nature, they are said to be more reactive. They are more reactive. So that is all about the polarity. But when we talk about the chlorine and chlorine, they both have the same electronegativity, right? This chlorine and this chlorine. So the shared pair of electron will be equally pulled by both the chlorine. So this chlorine molecule will be said to be non-polar, right? They won't attain any kind of a polarity or any kind of a charges on them like the hydrogen and chloride. So that is why we're calling them non-polar. And non-polar molecules are relatively less reactive in nature. Okay, so here comes that particular terminology. We have seen that the strength, if you have a carbon double bond carbon, it's more stronger than carbon single bond carbon. So carbon single bond carbon molecules are more reactive because the bond can break down easily as compared to double bond. So that is proved. Similarly, I told you that the sigma are more reactive than the pi are more reactive because they're weaker. Sigma are stronger and they can also rotate. So the pi can break easily. Now comes the polarity. So some of the molecules are polar in nature because of the electronegative difference, and some are non-polar because there is no electronegativity difference. So that is again a point where you can decide on the reactivity of the covalent molecule. Is the gist clear? Am I able to summarize the concept of polarity? So now
Yes.
let's go step by step and let's look at the definition of electronegativity, and let's see there is particular scale, right? Like for example, we have the periodic table. So in the periodic table, we have the elements with the atomic number and masses. So there is a scale which is known as Pauling scale. And according to that particular scale, all the elements have been given an value which is their electronegative value, which is a value which tells about their tendency to pull any shared pair of electron toward themselves. Okay, so let's talk about each of these step by step. All right, so let's go ahead. Okay, here we are talking about the electronegativity. Okay, here we are. And these are the learning objectives which I have taken from your book, and they are aligned with your syllabus as well. Okay, now let's go back to the electronegativity and its definition. They often give you the definition. So first of all, let's talk about the electronegativity and its definition. So we define the electronegativity is the ability of an atom to attract a pair of electrons toward itself in a covalent molecule. We are not talking about anything now. Right now, we are not talking about ionic compound. We are not talking about metallic bonding. We are elaborating on the covalent molecules, right? So this is your definition. Now, this phenomena, it gives rise to the positive, to a partially positive, like for example, I told you. So the electronegativity of hydrogen, as far as I remember, right? So electronegativity of hydrogen is 2.1, whereas electronegativity which has been assigned to chlorine is 3.0. So when they have a tug of war for pulling the shared pair of electrons, so chlorine, we can see its electronegativity is higher. So the shared pair of electron is pulled more towards chlorine, and that is the reason the chlorine will be getting a partially negative charge and hydrogen will be getting a partially positive charge. So this is going to make this molecule a polar molecule. Okay, so here this is they're saying this phenomena give rise to the positive nucleus ability to attract the negatively charged electrons, and the values are being assigned on the basis of the Pauling scale. So their values are assigned and they are being, like for example, right now I talked about 2.1 and 3.0. So these are the values which are being given on the Pauling scale. So here is the value, right? So we need to just remember for hydrogen, for fluorine, fluorine is the most electronegative element known, right? In the periodic table, fluorine is the most electronegative and it has a maximum electronegative value being given to it, and that's basically 4. The rest of the element have been given the electronegative value less than 4. Okay, so these are the only few elements whose electronegative value we are supposed to know, the one which I am putting a square around. So these are the elements because we will be talking about them in the organic. Now why are we studying so covalent bonding so much in details? The reason is that our topic 4 is basically organic chemistry, is related to organic chemistry, right? And all our organic compounds are basically covalently bonded, right? They have a covalent bonding in them. And when we talk about the covalent bonding, we will be talking about 2 types of molecules, and we will be talking about the intermolecular forces between the molecules, right? So if I have a methane and methane molecule, there should be some forces in between them. These we call intermolecular forces. So the type of intermolecular forces between the polar and non-polar is different. So their physical properties, their reactivity, all depends on certain forces, these intermolecular forces. Am I right? So we are just focusing on the elements whose which are the part of the organic chemistry. So we know that when we talk about the organic chemistry, carbon is for sure there. Then majority of the cases you have hydrogen, then oxygen is also there, then nitrogen is also there, then among the halogens, and we know the fluorine is the one whose electronegativity is the max. So these are the elements whose electronegativity we are supposed to kind of memorize, or as we work on them, we automatically memorize the electronegativity. I hope I'm clear. So we can see these are basically the non-metals with the maximum electronegativity of fluorine. Now it says that fluorine is the most electronegative. That means it's the strongest to pull the electron toward itself. Next we have oxygen, then nitrogen, then carbon. Now I hope I'm clear. Just an overview of what we have studied. We are studying about the covalent molecules, and we talk about there's so much mess on this on the screen on this page right now. We are just talking about the reactivity of the covalent molecules because soon we are going to study about the organic chemistry. And we said that the strength or the reactivity depends on the strength of the bond, the type of the bond, pi and sigma, and the polarity. Then I further introduced that the polarity depends on the electronegativity. So we are talking about electronegativity right now. Okay, so the definition is here. The electronegativity is the ability of an atom to pull the shared pair of electron itself toward itself, and there's certain value being assigned to the majority of the elements. That's on the Pauling scale, right? Now, can you see one thing, that all the metals, now which all metals do we have on the screen? We have the metal that's lithium, beryllium, and then we have sodium and magnesium. You can see that the electronegativity is too low. Am I right? The electronegativity is very low, whereas the non-metals, the electronegativity is high. Now, when you see the period 2 and the period 3, you can see certain trends in the electronegativity. Like we have done the trends in the ionization energy in the last class. What is the trend? What do you mean by the trend? Trend means pattern. So we can see there's certain pattern in the electronegativity when we move across the period. Okay, right. So electronegativity, we can see it's increasing. Initially for lithium, it's 1, then 1.5, then 2, 2.5, 3, 3.54. And same goes from sodium till chlorine, 0.9, 1.2, 1.5. So gradually it's increasing. Okay, in a period, across period, the electronegativity, it is increasing. And if you see the down the group, okay, this is down the group. In all these cases, when you talk about group 1, when you talk about group 2, down the group, it is actually decreasing. Am I right? So just like your, what you call it, ionization energy, the same thing used to happen with the ionization energy as well. Remember, what was ionization energy? You need to know the definition, and then we studied the trend. So when we were talking about the ionization energy, we said that it was increasing across the period. But when it goes down the group, it was decreasing. Am I right? So what were the factors which were responsible for the ionization energy? I said there were the trends in the ionization energy. When we
Yes,
were
yes.
talking about the period, the ionization energy was increasing across the period. And when we talk about the group, right, we said that ionization energy was decreasing. I'm asking, we talked about certain factors on which the trend was based. There were 4
Okay.
factors I talked about. So I'm sure you must have written down in your copies what were those factors through which we were explaining this trend. So the factors were basically the nuclear traction, right? Nuclear traction. And nuclear traction was basically because of the nuclear charges. Am I right? Then, because apart from that, there was a shielding effect. Am I clear? Right? So it was a shielding effect, that how many intermediate principal quantum shells were there. So the same factors which were the factors for the ionization energy, the same factors will be for the electronegativity as well. And we can see that the same way the electronegativity in a period, it is increasing, and down the group it is decreasing. Am I right? So we will be using the same factors and almost the same explanation to explain this trend as well. So this is nothing new. Am I clear? And these trends, these change in the atomic properties, we call this the atomic properties. These are the properties of an atom which atom possess. So we talked about one property, that was ionization energy, and we are talking about another property of an atom. We actually call them atomic property. I hope I'm clear. So one atomic
Yes, yes.
property we talked about, that was basically ionization energy. And today I'm talking about another atomic property which is possessed by an atom of an element, that's electronegativity. And they both had trends. And these trends we can explain on the basis of factors. Okay. Now let's talk about these factors. Look here. Now electronegativity varies across the period and the group, and the examiner will ask you why so. Okay, now in order to explain it, that during when it move across the period, it increases, and down the group it decreases. They will ask why so, right? What is the reason? So down the group, when we say it decreases, it says that electronegativity decreases. Now these are the reasons, these are the factors they are talking about. So the first factor they are considering is the nuclear charge. Now because the nuclear charge is increasing, what do you mean by nuclear charge? Remember what, that's wonderful understanding, but whenever you're going to write it down, remember the examiner is looking for the keywords. Keywords means the one which has been highlighted here. Can you see the highlighted words here? Right? So these highlighted words should be used in your explanation. So I'm asking you what is a nuclear charge, but the examiner will not ask you what the nuclear charge. They will say that why the down the group the electronegativity decreases. So these are the phrases you'll be writing. The nuclear charge increases, right? So in down the group, the shielding effect is also increasing, but the shielding effects, it outweighs the nuclear charge. So shielding effect is having a greater impact as compared to the nuclear charge. So the shielding effect having a greater impact So because of that, what will happen? It's easier. Now they are not asking about the ionization energy, they are asking about the electronegativity. Electronegativity is pulling of the electrons because the nuclear charge, it increases, but the shielding effect, it outweighs. Therefore the nuclear attraction, that means the protons in the nucleus, nuclear attraction, it decreases. Because the nuclear attraction decreases, so to pull the electron toward itself is difficult, and that is the reason the electronegativity decreases down the group. Am I clear? Decrease in the attraction between the nucleus and the bonded pair, and that is the reason that the electronegativity decreases. So please look for the keywords. So nuclear charge, we don't have to explain because they give you just 2 lines to explain the trend, right? So these keywords should be the part of your answer. So nuclear charge increases, the shielding effect, that also increases, which outweighs the nuclear charge. This makes the decrease in the attraction between the nucleus and the bonded, and that is why the electronegativity decreases. I hope I'm clear. The nuclear charge is actually the number of, yes. So they will never ask you the definition of that. Its nuclear charge depends on the number of protons in the nucleus. So as you move from left to right in a period, the number of protons increasing because the atomic number is increasing. So the nuclear charge is gradually increasing. Am I right? So nuclear charge is all because of the protons which are positively charged. Fine. So this is what a pictorial depiction of the electronegativity trend in a group. So this is a trend of electronegativity down the group, right? So these are the factors they're stating. The number of shell increases, more shielding. Now, we are not doing the atomic radii right now because we have not touched upon it. Then we have the increase in the nuclear charge is negligible because the shielding, it outweighs, what do you call it, the nuclear charge. And therefore, they will be experiencing less attraction. And that is why this is. So these are the keywords which should be a part of your explanation. So this is what we have done. Now coming to the across the period. Now, as we have explained, in the case of the ionization energy, when you move left to right, it was increasing. Using the same factor, we can explain the electronegativity as well because that too is increasing. So electronegativity depends on the nuclear attraction. Okay, and the nuclear attraction in turn depends on the nuclear charge, right? So when you move left to right, what is happening? The nuclear charge is increasing. And forget about the atomic radii, we are not touching on it. And because the nuclear charge is increasing and there is the same shielding effect, am I right? Same shielding effect means because you're talking about the same period. So there is no more in between principal shell being added. So there is the same shielding effect there, right? So as you're moving from left to right, so because of the nuclear charge is increased, there's a greater attraction between the nucleus and the bonded electrons. So that is why as you move across the period, the electronegativity, it increases. I hope I'm clear. So these are the key factors. These are the wordings. These are the keywords which will be used in explaining the reason why electronegativity increases across the period. Okay. Are you taking the snapshots of the pictures of the PowerPoint? Are you taking? So these are the basically the reasons. On the basis of that, you will be explaining the trends down the group and across the period. So these are the keywords. These are the basically factors you will be using. So this table is clearly specifying, making a comparison there. Moving ahead now. Coming to the next part, that's the electron density. So we understood now, before we move on to the electron density, now I'm going to explain here when we talk about the electronegativity, as I already explained you, that if we talk about carbon and if we talk about the chlorine and chlorine, if we talk about the chlorine molecule, as I told you, its electronegativity of both the chlorine is 3.0. So the shared pair of electron is equally pulled by both the chlorine there. So such molecules are said to be non-polar. But if we have the hydrogen and chlorine, hydrogen was said to be 2.1 and chlorine was 3. So this being more electronegative is going to pull the electron toward itself, and that is the reason The chlorine will be partially negative and hydrogen will be partially positive. When there is a polarity being developed, the partial positive, the shared pair of electron is pulled more toward one element. We call such molecules are the polar molecules, polar covalent. And the polar covalent molecules are said to be more reactive in nature. Is it clear, beta? They are said to be more reactive in nature. Fine. And we normally represent them, we normally show them by a arrow, which is also known as a dipole. Okay, this is known as a dipole. Dipole is a vector quantity, right? Being a vector, you can add it, you can subtract it, right? And it has a direction also. So it has a direction as well. So whichever the element is more electronegative, we'll be showing it by this way. And this is going to be a negative terminal. This is going to be partially positive. So we represent a polar molecule in this form. So it's clearly stating that here the shared pair of electron is more toward chlorine, and that is why it's acquiring partially negative. This is acquiring partially positive. We know the reason very well. This is 3.0 and this is 2.5. So automatically the values are also stating that this is a risk. Similarly, between hydrogen and oxygen, it's again 2.1 and 3.0. So it's the shared pair of electron is moving more towards oxygen, partially negative. Then same case for nitrogen, it's more electronegative. So the shared pair of electron is toward this side, right? Is it clear? So that is how the polar covalent bonds or the molecules are being formed. Okay, good. So till now in O levels, we have studied distinctively. Okay, we have just three kind of bonding. One is your ionic bonding, another one is your covalent bonding, and the third kind was metallic bonding. And we have defined three different categories. Now here they're saying that this category can blend with the ionic characteristic, because when we talk about the polar molecules, so this polar molecule is, if there is a polar molecule, they tend to have certain characteristics of the ionic compound because they're polar in nature. Like for example, if we talk about hydrogen, it was partially positive, it was partially negative. So because of the electronegativity difference, so it's certain characteristic, they get some characteristic of the ionic compound as well. Now here they're saying that polar covalent molecule can be thought of as being two ideals of the bonding type. It's a combo. It is the covalent molecule, but some of the characteristic of the ionic it has developed, because here my atoms, they are partially positive and partially negative because the shared pair of electron has shifted towards chlorine and it has developed a polarity there. Okay, so if the electronegative difference is large, if this large, then the compound is said to be ionic, right? So if we normally say that, I'm just going to show you the slide. So generally we say that if the electronegative difference is greater than 2. Look here, if the electronegative, this delta means the difference. So if the electronegative, generally we say that if the electronegative difference is greater or equal to 2, then the compound will be formed that's ionic. Okay. If the difference is between 0.5 less than 2, if it range between 0.5 and let's say less than 2, that's 1.9 something, less than 2, then it is going to be polar. Okay, and if it is below, and it is less than, if it is ranging between 0 and 0.5, we call the substance to be non-polar. I hope I'm clear. So this is what I make my students understand. In your book, they have given this kind of a table: the electronegativity difference and the percentage ionic characteristic. If there is no zero difference, then the characteristic, how much percent ionic characteristic is there, it's 0. That means that substance is not ionic, it's covalent. Okay, so here there's telling you that as the electronegativity difference is increasing, till here they're saying, look, the ionic characteristic is 63%. When the difference is around 3, so 89% ionic characteristic it has. So in a way, this is a data they have given slowly and gradually how the ionic characteristic is increasing. but we need to know the difference. So if the elements which are belonging in a compound, those two elements, if I talk about, let's say I have a methane. Okay, the methane, I have a carbon and hydrogen. Carbon is basically 2.5 and hydrogen is 2.1. Then these molecules are going to form a non-polar. Is that clear? So here they have given you the example. So all the alkanes which have carbon and hydrogen only, they will be said to be non-polar. They are completely covalent. They are non-polar because the electronegative difference is less than 0.5. So if it is less than 0.5, then they are said to be non-polar. Their reactivity will be different from the ones which are polar in nature. Like for example, I have another example. We have CCl4. I have a carbon which is 2 point how much 5, and I have 3.0. So it's 0.5, right? So 0.5 will make it a polar molecule, right? So this is there is one more thing which we'll be learning about CCl4, but right now I'll not cover it up. So, right? So we broadly see that if the electronic difference is ranging between 0 to 0.5, less than 0.5, they are non-polar. If it ranges between 0.5 less than 2, then they are polar. And if the difference goes beyond 2, they are basically said to be ionic. I hope I'm clear. So here they have given you the example. The electronegativity of sodium is 0.9 and of chlorine is 3. So the difference is 2.1. So it's completely ionic. Now, in the case of HCl, the difference is 0.9. It's polar. In the case of hydrogen, both the hydrogen atom has the same electronegativity. It's totally non-polar. So this is how we decide on. Okay, so this part is done. So difference in the Pauling electronegativity value can be used to predict whether the bond is covalent or ionic, and if covalent, whether it's polar or it's non-polar. Okay, going ahead. This is all explained. This is done. So let's talk about when an atom, you can take a snapshot of this because this is, I have already explained. They're talking about the polar covalent molecule, already explained that they're going to acquire a partially negative charge and partially positive charge. Taken? Can I proceed? Okay, good. Taken snapshot of this as well. Now they're talking about the electronegativity and the ionic compound. They're saying that they're what I told you, the electronegative difference is greater than or equal to 0. So those are going to form the ionic. So this is basically in words, but I actually showed you on the slide above. Fine. This is a checkpoint. It's a part of your book. Okay. Now they're saying, I'm just reading out the question and I think it will make sense now. Suggest why the electronegativity of fluorine is greater than that of chlorine. They're talking about the trend in a group. They're talking about the trend in a group. Now, why fluorine is more electronegative as a chlorine? As I talked about that on the basis of nuclear charge, nuclear attraction, shielding effect, these are the two key factors. You'll be taking these two factors into account, explaining why chlorine has a less electronegativity. You'll say that the nuclear charge is increasing, but is being outweighed by the shielding effect. The number of shells are increasing, which reduces the nuclear attraction, and that is why the electrons cannot be pulled strongly, and that is why the electronegativity decreases. We have already discussed this. Then coming to the next question, ionic bonding and the covalent bonding are the two extreme of the chemical bonding. Many compounds are intermediate in the characteristic. Give an example in each case, explain what is meant by the ionic bonding and the covalent bonding. I think you can easily do it. Now select a compound that has a bonding of an intermediate characteristic and character and explain why it has this type of bonding. So here you can explain about HCl, okay? Or because I told you which you can, they basically asking you about the polar molecules, right? The polar molecules are basically in between the ionic and the covalent, non-polar. So you have to give the example and you will talk about the difference of electronegativity and they're acquiring a partially negative and the positive characteristic, right? Coming to the question number 3, place the following bond in order of decreasing polarity. Space, that is the place plays the most polar first. So you will talk about the dipole moment. So carbon, you'll look at the difference, 2.1, and bromine, I don't remember. Let's go back onto Pauling scale as well. Bromine must be lower than this, okay, because bromine is down there, and it's there. The scale, the Pauling scale is there in your book as well. So it's less than 3. I don't have the exact value. Okay. So look it from your book and look at, have they given bromine? They have not mentioned here. No. So you can take it from the book. The book must be having that. So you will find out. So if you talk about the decrease in polarity, we know that the difference 2.1 and 3 is there. Then 2.1 and 4 is there. And look here. So we have fluorine, chlorine, bromine, and iodine. So as you go down, the electronegativity also decreases. So if you have a chlorine, fluorine, chlorine, carbon, fluorine, carbon, chlorine, carbon, bromine, carbon, iodine. So as you go down, the electronegativity is decreasing. So the difference is also, the electronegativity difference is also decreasing. So the maximum electronegativity difference will be between the max. This is going to have the max. Okay. So if we want to arrange it, so we'll have the carbon fluorine, which is going to have the in the decreasing polarity. That means the one with the maximum first. Then after carbon fluorine, we'll have carbon chlorine, then we'll have carbon bromine, and then we have a carbon iodine. We don't need the values here. We can simply guess because we know that in a group, the electronegativity decreases. Other questions clear? Beta, ionic bonding is absolutely, we define that the ionic compounds are those compounds which are formed between a metal and a non-metal. Okay, there is between a metal and a non-metal. We always, the ionic compound is being formed between a metal and a non-metal, right? So like for example, we have NaNCl, and that also because of the transference of electron, because the electrons are being transferred, so one acquire positive and one acquire negative, and the electrostatic force between the positive cation and negative anion is known as ionic bonding. Now we have the polar and non-polar molecules. They are a part of the covalent bonding. Now the covalent molecules, they can be polar or they can be non-polar. So basically covalent is about the sharing of the electrons. Here in ionic, there was a transference of electrons, right? Because one was metal, it has an excess of electrons in its last shell, so it has easily given it to the non-metal to satisfy its to become satisfied as noble gases. So easily the electrons were transferred. But when we are talking about the covalent is all about the sharing, and the sharing between the non-metals only. Okay, and these non-metals sometimes they acquire a polarity on the basis of electronegative difference, right? When the electronegative difference is higher, they become polar in nature, but the sharing is taking place between the two atoms. But when the electronegativity difference is lower than 0.5, sharing is definitely there, so they become non-polar in nature. They are the part of the covalent bonding only. So polar and non-polar are the covalent molecules, but they are acquiring a slight characteristic of the ionic compounds. They are attaining a polarity. That means, like for example, in HNCl, this is acquiring partially positive, this is acquiring partially negative. So some of the traits of the ionic compounds they are acquiring, right? Though they are covalently bonded. Understand? Initially, we studied that the different compounds, ionic, covalent, we have categorized them under 3 different categories. But now we are talking about the blending, the merging of those things together, right? The cusp between them. Okay. All right. So here we are done. Now we move on to the bonding in, okay, this particular part I am not explaining because this is already done in O levels. So they're asking you to have a dot and cross diagrams. You can easily do it. So this is your learning outcome, the learning objective. Understand what is meant by the term simple molecules or the discrete. Discrete means simple covalent molecules, right? And draw a dot and cross diagram. You very well know how to draw a dot and cross for a single, double, and triple bond. and also show a displayed formula for them. I'm just scrolling down and I'm sure you can easily do it. Can you do this kind of a dot and cross? No issues here, right?
Yes.
Hello, yes. Okay, good. This is again very simple. So they're talking about dot and cross and they're talking about displaying them with in the displayed formula where you're showing them by a bond. Where they have a double bond, you're showing double bond. Where there's a triple bond, you're showing triple bond. So this is a displayed version, displayed formula, and this is a dot and cross. Okay, you can do it very well, I'm sure. Now, further, when we talk about the simple molecules, then there are certain exceptions there. Okay. Now, the bonding take place, whether the covalent bonding or the ionic bonding take place, because the elements they want to be like noble gases. Right or wrong? The bonding we started off, we study that the bonding take place because they have the metals, they have an extra electrons in the outer shell which they can easily lose and become like noble gases. The covalent molecule, the non-metals, they need to acquire, isn't it? And so basically what happens here, we are specifically talking about the covalent molecules only. So when the covalent compound is being formed, they try and have the complete octet there, isn't it? 99% cases we have seen, they are basically acquiring an octet. If we are talking about the carbon dioxide, so carbon has how many electrons? 4 of its own, and it's taking 2 from this oxygen and 2 from this oxygen. So 4 of its own, taking 2 from this oxygen and 2 from this oxygen. So carbon octet is complete. And same ways, the oxygen has 6 of its own, taking 2 from this. Its octet is complete. Same ways, it has 6, sharing 2 from this. So basically, majority of the compounds, when we see as a covalent compounds, their octet gets completed. Now here we are seeing that certain examples, certain compounds, they do form covalent compounds, but somehow they are exceptional. Their octets are not complete. Okay. Now it says that this is not always true, as you can see from the examples which are given down here. The outer shell of the central atom, they're just talking about the central atom, right? There they do not have, though they are covalently bonded, but still they are lacking in the 8 electrons. They are not completely satisfied. The last shell doesn't have 8 electrons. So the first example is BCl3. So BCl3 is an exception where beryllium comes from group 2. So it is coming from 2, it has 2 electrons and it's sharing 1 electron from each. So the central atom has got just 4 electrons. Then we have BCl3, boron trichloride. Boron belongs to group 3. It has 3 electrons of its own and 3 electrons coming from 3 chlorine. So it has altogether 6 electrons. Then we have phosphorus pentachloride. Phosphorus coming from group 5. It has 5 valence electron. Here, what is happening? 1 electron per chlorine is coming. So it is exceeding the number that has 10 electron. So they are short and this is exceeding. Same goes for sulfur hexafluoride. Sulfur coming from group 6 and each fluorine is giving 1. So valence electron in this case are 6 and the 6 electrons, 1 each coming from the fluorine. So the central has 12 electrons altogether. So the first 2 cases, they have a lesser electron, lesser number of electron in the outer shell, and here this is exceeding. So these are certain exceptions here. Okay. Now we have a dot and cross diagram. This is going as your homework, and displayed formula also. Right. With that, I'm leaving the meeting. That's all for today.